All right, are there any questions?
Yes.
Uh-huh.
Are we doing titration today?
No.
We're just like preparing for the titration lab.
Yeah, we're preparing for the titration lab. That's why I have titration lab up here. Yeah. We're going to lecture for the first part, and then the second half we'll do the lab. Which lab are we doing today? Hydrolysis. We're going to do the titration lab on Tuesday next week. Because the exam is going to be on Thursday. Normally I'd like to have it flipped. I'd like to do the titration on Thursday because then I can talk about it on Tuesday. But since I'm not going to be able to talk about it beforehand, I'm going to talk about it today, the titration lab. The titration lab, the titration lab, a lot of people screw up on. So I don't have a procedure, a written procedure for it. It's not a difficult lab. It's not in the catalyst. But it's something you have to think about. And so what are we doing in a titration lab? We're just plotting the pH versus milliliters of sodium hydroxide. And so we just need to collect data. As we add sodium hydroxide, we just measure the pH. But the first data point here is just going to be your acid with no sodium hydroxide. And the acid is going to be a organic acid, which is weak. And so we have the unknown weak acid. And so the pH is going to start kind of high, not as low as something like a strong acid. So the first thing is, the pH of the acid, does that depend on how much water you add? The unknown acid itself is a solid that we weigh out. And so does the pH of a solid unknown acid depend on how much water we add? Yes. Right. And so the initial pH depends on how concentrated or how dilute you make the solution, right? The more concentrated. In fact, if you make it way too dilute, the pH will start to approach pH 7, right? If it's diluted to the extreme. Well, our initial goal in this is we want to dissolve the unknown acid in a minimum of water. Why do we want to dissolve it in the minimum of water? To start at the lowest pH possible. Because what happens is if you have it too dilute, the pH curve is supposed to, let's say the pH curve is supposed to look something like this, just as an example. But if you make it too dilute, like this, then this rise in pH here isn't going to be as pronounced. And let's say we made it way too dilute. If we make it way too dilute, you might not see much of an equivalence point. This first wave here is the equivalence point. And so to make this first wave here as pronounced as possible, we want to make sure we start at the lowest pH possible. And so try to dissolve your unknown in a minimum of water. Oftentimes we do that, we try to make it more concentrated rather than less concentrated because usually you get better signals from more concentrated stuff. In this case, maybe pH readings or whatever else. But there could be a problem, and that is if you dissolve it in a minimum, this is a pH titration, and we have a pH probe that we need to stick in the acid, like this. And the pH probe is going to have a little glass bulb at the bottom. And this glass bulb has to be completely submerged. And so if it's only partially submerged, then you are not going to get accurate readings. And so if we dissolve it in a minimum and we see that the glass bulb is not completely submerged, then what are you going to have to do? You're going to have to add more water, even though that will hurt you. But the problem is we have no choice because of our probe. Now, if we had a micro probe, or they have different designs of probes. Probes without a glass bulb with a little semiconductor chip there. Then we might be able to get by, but we can't. We have to have enough water to completely submerge the glass bulb at the end of this. Well, let's say your unknown is very difficult to dissolve, and you keep adding water, but you're afraid it's going to take way too many milliliters of water to get it to dissolve, because barely any of the crystals actually dissolve. So rather than adding 100, 200, 300 milliliters of water, you better stop and then try to dissolve it some other way. And so what's a technique that might help you dissolve, increase the solubility? Heat it, right. And so if your unknown doesn't dissolve, try heating it on the hot plate. You heat it on a hot plate, you get it close to boiling, stir it, it should dissolve. The problem is do you want to titrate a hot solution? Hot solution is going to mess up the pH. And so what you want to do is cool it back down to room temperature or close to room temperature by either running cold tap water on the surface of the container or getting ice from the stockroom, cooling it in the ice bath. That should bring it back down. All right, not only are we going to have a pH probe in the beaker, but we're going to have a stir bar, which is a Teflon-coated magnet. And the Teflon-coated magnet goes in there because we're going to have this sitting on a stirrer, magnetic stirrer. With a magnetic stirrer, we just turn this knob and it starts spinning this, so we don't have to swirl. Do you guys remember swirling your Erlenmeyer flasks? Erlenmeyer flasks are easy to swirl because it doesn't splatter out, but if you were to swirl a beaker, then you have more difficulty. And so we're just going to stir this electrically. All right, then we'll start adding. Now, there is something called sampling frequency or resolution. High resolution, low resolution. And so what we want to do is we want to get this image of the titration curve, and we want to get as high resolution of an image as possible. That is, we want to see this in high precision with good clarity. In other words, the best thing is to sample this very frequently at very small intervals. And so if we sample this, we'll add one drop, let this stir, equilibrate, record the pH. And then add another drop, stir, let it equilibrate, record the pH. If we did this drop by drop, we'd get excellent resolution, probably the highest. We could go half a drop. But the problem is that's a lot of time and a lot of data. We don't have enough time to do that, especially in a titration. What's the volume of titrant that we're going to use? The volume of titrant is going to be up to 50 milliliters. Our burettes can hold up to 50 milliliters. And so 50 milliliters drop by drop, you're not going to finish in time. And so what we want to do is we want to get high resolution, that is a lot of data where things are changing. But we don't have to collect a lot of data where things aren't changing. And so, for example, here, this is a buffer region. It doesn't change much. And so we can spread out the sampling interval. But when we start getting close to the equivalence point, we don't want to spread it out because this equivalence point happens in a few drops, you know, boom. One drop we're here, and then 4 drops later we're at the top. And so we have to be careful, because if we have a wide interval here, we're going to completely miss it. We don't know exactly where it popped up, you know, with good precision. And so when we get close to the equivalence point, we got to tighten up the sampling frequency. That is, we take samples at much smaller intervals. These could be 1 drop intervals here. 1 drop, 1 drop, 1 drop. And then we're up here. And then up here, where it kind of flattens out again, and nothing much is happening, we can widen the interval. Especially, we aren't going to stop at the equivalence point or the end point. We're going to just keep going past it until we see it's not really changing much up here. And so we can jump up to much larger intervals near the end of this. And so the problem is when do we slow down? Because, you know, if you overshoot this by a drop or 2 drops, it's already gone. You know, it's done. And so when do we slow down? You know. And so that's a big question. And so when you slow down, well, have no idea. Because, I mean, how many grams of unknown acid do you use? That varies, right? The people are going to weigh different amounts. If they weigh different amounts, then where we slow down is going to be different for each person. And so this type of titration is very time consuming. And so before doing this titration, what we're going to do is we're going to run a trial titration. And a trial titration is going to be exactly like what you did in Chem 1A. You know, you weigh out the sample of unknown acid into an Erlenmeyer flask, dissolve it, add a couple of drops of phenolphthalein, and then titrate it to the end point. And so in a trial titration, we're going to use an Erlenmeyer flask for this. We aren't going to use any kind of pH meter. We're going to weigh some unknown in here, but how much unknown should you weigh out? Because if you use too much unknown, you know what's going to happen? Yeah, it's going to take longer, and you're going to have to refill the burette because you might go over. You know, I had one student who transferred it to a larger container. Eventually, was at a 600 milliliter beaker, and the 3rd load on the burette. You know, 3rd sodium hydroxide fill. And so you don't want too much. And then, if you don't want too much, then you might err on too little. What's the problem with too little? What the problem with too little is relative error. Relative error is, you know, if you're weighing out a very small sample, then any little error, like a dust particle falls on there, leads to a huge error in your analysis. And so the same thing happens with titrations. If this titration only took, let's say, 1 milliliter, 1.12 milliliters to reach the end point, then that's like 23 drops or something. 23 drops. If your titration is off by a drop or 2, 1 drop error when you only have 20 drops is a huge error, right? It's like 5%, 6% error. Versus a 1 drop error when you're using a lot of solution, like 40 milliliters, isn't so bad. So 1 drop error in 1 milliliter versus a 1 drop error in 40 milliliters, a 1 drop error in 40 is much better in terms of relative error. And so we don't want to use too little. We want to use just the right amount, but you have no idea what just the right amount is. And so when you get your unknown, you're going to have a suggested sample size there. That's not the sample size that you want to use. That's just suggested, so you don't have to waste a lot of time guessing. You know, guessing and then trying it, guessing and trying. And so you use that, it should fall between 0 and 50 milliliters, right? But the optimum is this. When we hit the end point, we'd like this to be roughly 30 to 40 milliliters. And so let's just shoot for 30 milliliters here. So if your trial titration took only 10 milliliters to hit the end point, then you want to use 3 times that mass for your pH titration. If your trial titration took like 45 milliliters, then you better use like the same amount? No, less. For sure you want to use less. Why? Because you're going to cut this short. It's going to look like you chopped off part of it, the end part. You need to see where the wave goes up and then flattens out, right? And so you don't want to use too little. I've seen these where the data ends here because I think I mentioned this yesterday. Their titration curve looks like this after they plot it. What happened? What happened was they stopped when it turned pink, and they thought they're all done, so they wrapped everything up, and then they had to repeat it. And that's why I want to use the entire lab period on Tuesday, because every semester this kind of stuff happens. That somebody has to repeat it. And so And so this is why we're going to target 30 for the endpoint equivalence point, and that gives us another 20 milliliters that we can collect more data past the equivalence point. Obviously it's really going to flatten out, so we can increase the interval. Okay, so we're going to run the trial titration with just phenolphthalein. On some grams of unknown, and therefore we'll have the milliliters of base to grams of unknown ratio, and then we can calculate the optimum sample size here, and then run our titration. If we know that our equivalence point is going to come around 30, then before 30 we better slow down, right? Do you guys remember the like at about 15, if this is monoprotic, at about 15 milliliters, the pH should equal the pKa. If we go pKa plus 1, then we're at what equivalence point? pKa plus 1 is the 10/11ths? That's right, 10/11ths. So if we're at the pKa, let's say you're at 15 milliliters and you see the pH, and the pH is increased by 1 pH unit, how much more do you have left? Very little, 1/11. And so for some reason people say, oh, my pH has only climbed by 1, but then they think they're safe. And then boom, they missed it. They missed it because they're at the 10/11ths equivalence point. They only have 1/11 left, which is nothing. And so if you see that, you better start to slow down, drop by drop, if you aren't already. And so when we get close to this, we need to collect a lot of data, as I was saying. This rises so steeply that it's kind of spread out, but I'll try to illustrate it like this. We collect a lot of data here. That way we can pinpoint the equivalence point easily. Okay, this is for a monoprotic, but you know what? You might have a diprotic too. If you have a diprotic acid, it's going to look a bit differently. And so when we titrate this with phenolphthalein, if we have monoprotic acid, we're titrating it to the equivalence point, because if we have a weak acid, let's take a look at phenolphthalein. Phenolphthalein changes color around where? What pH? Yeah, the pKa is about 9, so the color change, where it's a mixed color, intermediate color, is from 8 to 10. 8 to 10, pKa plus or minus 1. And so this is going to start turning light pink at about pH 8. And so if we're looking at monoprotic, the equivalence point here, what's the pH at the equivalence point? No. The pH is going to be greater than 7. It's only for a strong acid, strong base that you have a pH of 7, like sodium chloride. This would be something like sodium acetate. So the pH is going to be greater than 7, which means that phenolphthalein is going to be colorless, colorless, colorless until we hit about here. And then it starts to turn light pink, which is good. That shouldn't lead to much error because there's very few drops from the beginning to the end of this rise. And so for monochrotic, then we know where the equivalence point is roughly, based on phenolphthalein. But what about a diprotic? For diprotic, there are two equivalence points. And for just spread it out a little bit. The first equivalence point is less pronounced than the second equivalence point, typically. But the first equivalence point here, which is around this area, the first equivalence point has a pH that's actually less than 7. So it's in the acidic part. And the second equivalence point has a pH greater than 7. So if you're titrating a diprotic acid using phenolphthalein, you never see the first equivalence point. It's going to be colorless, 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 colorless until you hit this high enough pH. And here's where you're going to start to see. And so with a diprotic acid, phenolphthalein turns pink at the second equivalence point. For monoprotic acid, it turns pink at the equivalence point. Since this is an unknown acid, we don't know, is this a diprotic acid or a monoprotic acid? It can't be triprotic. We have no triprotic acid that you're going to get. And so the only two choices are it's monoprotic or diprotic. In Chem 1b, we can tell the difference by looking at the shape of the titration curve. In Chem 1a, you're told, if it's monoprotic or diprotic. But sometimes telling by the shape is very tricky. You know why? Telling the shape is, number one, this first equivalence point is not very pronounced. Number two, what happens if you have to add more water to submerge the... It becomes more dilute. And, when you're adding base, the pH can't go down. When you're adding base, the pH has to go up. And so there's only going up from here, which means that this first equivalence point is barely a blip. And in fact, if it's too dilute, what's going to happen? You're not even going to see it. And so this is why, there is a procedure for this. Maybe some of you might have seen it, but the procedure says add this many milliliters of water. When you add that many milliliters of water to your acid, it can be way too dilute, and you don't even really see this first equivalence point, which means a lot of people get it wrong. And so the data collection is simple enough, so just try to explain it here. Make it as concentrated as possible to drop this down to make this as pronounced as possible, because it's not a very big jump. For triprotic acids, this happens on the opposite end too, because for triprotic acids, it's very difficult to see the third equivalence point because of the same type of stuff, dilution and concentration, right? And so in phosphoric acid, the third equivalence point is never seen because of dilution and concentration, low concentration, not enough concentration. Well, anyway, it happens here on the front end too. So there are some critical points. For Tuesday, all we're doing is collecting the data. We aren't going to analyze anything. But when we're collecting data, we have to be careful to make sure we get good data. So for example, if this is a monoprotic, you want a lot of data around 15. Do you know why you want a lot of data around 15? Well, for monoprotic, the curve is flat. This is right in the middle of the buffer region. but we still want a lot of data even though this is flat. Why? Because at 15 milliliters, the pH is equal to the pKa. This is an unknown acid. And so if we know the pKa of the unknown acid, then yeah, we might be able to determine the acid. The same thing goes here. You know, in the middle point here, we get the pH equal to the pKa1. And in the middle point here, in the buffer region 2, we get the pH is equal to the pKa2. Now, sometimes the pKa1 matches better, sometimes the pKa2 matches better with the data. Which one is more reliable, do you think? pKa1 or pKa2? Which one would you trust more? pKa2? Why?
It'd be hard to detect the first one.
It could be hard to detect the first one. The first one's going to be more prone to error because of
Dilution.
yeah. Well, nonetheless, we want to collect a lot of data, and so there's going to be points that we need to collect a lot of data. And so let's break it down because we don't know what we have. We could have a monoprotic or we could have a diprotic acid. We just don't know. And so let's say we have a diprotic acid. Well, diprotic acid, what we want to do is we want to collect a lot of data here at about 15 milliliters because that's where we expect to see the first equivalence point. And then when we want to collect a lot of data here around the second equivalence point, 30 milliliters. And so we need a lot of data here and here. You get the first and the second equivalence point. But for a diprotic acid, we also want to pinpoint pKa1 and pKa2. So we need a lot of data around here and a lot of data around here to be able to see it. Okay, once this curve starts flattening out, then we can spread out the data. Take much wider intervals. Okay. Since you don't know if you have a monoprotic or diprotic, that means we're going to have a lot of data here for monoprotic and a lot of data here for monoprotic, which isn't really necessary, but we're collecting it in case it's diprotic. And so where do you need to slow down and take more data? Well, at 15 milliliters you do. Where else? 7.5, 22.5. All right, from 0 to 7.5, we can take wider intervals. So maybe we could go 1 milliliter intervals, you know? But not to 7.5, we have to stop before 7.5 because our trial titration might not have gone so great, etc. And so we can collect data at wider intervals, you know? Up here, we might spread it out, 2 milliliter to 4 milliliter intervals. But near the equivalence points, we need to collect data at what interval? 1 drop intervals. 1 drop intervals.
But like if we, let's say we do have a diprotic unknown, you take out the phenolphthalein doesn't detect the first equivalence.
The phenolphthalein doesn't. That's why we're generating this pH curve. The pH curve will be able to detect. You'll be able to see it. The phenolphthalein, you'll add phenolphthalein to this. You could add it if you want. It'll be colorless, 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 pink. And so phenolphthalein just tells us one point on the curve.
So the different pHs that we reported.
Yeah, you can visually see it, you know. What's happening around 15? Is it staying flat or is it increasing? You could easily see it. You know, even before you graph it. You'll have an idea. All right, it depends on how much confidence. You know, some people, when they do the trial titration, they use a very small amount. I've seen trial titrations like this, and it only takes like a milliliter to hit the endpoint. You know, 1 milliliter to hit the endpoint. 1 milliliter is how many drops? Roughly.
30.
No, 20 drops. 1 milliliter is roughly 20 drops. It's not accurate, so don't use that. You know, but 1 milliliter is about 20 drops, roughly. That means if they had a couple of drops error in the hitting the endpoint, maybe they overshot a little bit, right? What does that mean here? You know, a couple of drop error here means huge error here. And so, you know, if your child titration didn't go that well, you know, you might just redo it because it's quick and easy to do. You know, the more milliliters, let's say your trial titration took like 30 mils, then, you know, 1 drop error there is not that big of a deal. You know, it's not going to translate to a huge error over here. And the huge error meaning that, hey, you're at 29, or you're planning to slow down at 29, but the equivalence point shot up at 28. This happens all the time. Or people slow down at 29 and they're collecting drop by drop, and it doesn't happen until 32, 33 because their trial titration wasn't so good. Right? And so they end up taking a lot of time collecting a lot of data. Some people, it goes so smooth, you know, it's less than an hour and they're out of here. But I'm going to schedule the full entire lab period because, you know, that's more the exception. And most people take close to the entire lab period, and a lot of people take more than the entire lab period because they're redoing it. Okay. Well, any questions on this? No? All right, this lab, you're going to write a formal scientific lab report for. You know, explaining how you determine what your unknown acid is, which factors. Because you're going to have the pKa's, you're going to have the stoichiometry, that is, we can calculate the molar mass, we have the grams of unknown. We can figure out the moles of unknown by the equivalence point. You know, at the first equivalence point for diprotic, the moles of acid equals the moles of base. At the second equivalence point, the moles of acid equals 2 moles of sodium hydroxide, the 1-to-2 ratio. For monoprotic, it's a 1-to-1 ratio. And so from that stoichiometry, we can get the molar mass. So we'll have molar mass and pKa's to help us in determining. You might get lucky and everything matches up nicely. Or you might get unlucky and nothing matches up. And so what do you do? A lot of people like to repeat it, but it's difficult to repeat this, you know, to redo it. And so, you know, oftentimes that's the case. You don't have enough time, so you just got to take the data that you have and analyze it the best you can. And then just come up with the most reasonable, you know, the most well-argued identification for your unknown. And so that's why I like the formal lab report, because the formal lab report, you aren't just saying, well, this is the acid I found, you know. The formal lab report, you're going to discuss it so that in case you screw it up, at least you can recoup some of the points, you know, if your arguments are pretty sound. Well, anyway, let's continue with this. That's this. I'm not sure if I'm going to collect a rough draft for the titration formal report, but I am going to collect a second draft for the synthesis lab. And so, if you didn't catch this, I'm going to collect this after spring break, Tuesday. And not just a discussion, but complete as much of it as you can, all the sections, and I'll take a look. Now, I didn't really comment on some of the sections like experimental, but some people have the experimental wrong in terms of tense and other stuff. I'll look at it. You guys turn that in. All right. I want to just talk about this fractional precipitation problem before the weekend here that we were talking about earlier, I think. Or were we talking about that earlier or not? Oh, no, we didn't get to it, huh? Okay, I want to talk about percent precipitation. Were we talking about that? Did we finish that calculation on percent precipitation? No?
Percent remaining.
Okay, did we do the percent remaining?
Yeah, we got to percent precipitation equals the percent remaining.
Okay.
Oh,
Oh, we didn't actually calculate it. Okay, let's go ahead and calculate it from the data that we had. So this brings up the point that was made, how much is enough? And so let's see how much this comes out to. So let's calculate the percent remaining. The percent remaining is just equal to the equilibrium over the initial. And is this the reset initial or the original? Original times 100%. And so how much did we have at equilibrium? Was it calcium? How much calcium did we have at equilibrium? 8.28 times 10 to the negative 9. That's the molarity at equilibrium, and the initial we had is 0.100 times 100%, which means what does this come out to? 10 to the positive 1, 10 to the minus 8, 10 to the minus 6. So 0.00. 0.50828% remains in solution. And so the amount that precipitates, the percent precipitation, is just 100 minus that. So we started off with 100%. We only have this much left over. So that's 1, 2, 3, 4, 5 zeros and an 828. So I need 5 zeros here, 6 zeros, 7 zeros, 8 zeros. And so this is going to come out to 99.9999172% precipitation. Is that 100%? No, but it's awfully close. How close is close enough to 100%? Well, it's not really ever going to get to 100% precipitation. And so we need a cutoff. And so your book's cutoff is this. Your book says that 99.9% precipitation equals complete precipitation. It's not really complete. There's going to be a little bit left over, but they'll call it a complete precipitation. And so it turns out, if we added the 0.400 molar hydroxide, sodium hydroxide, then we get pretty much complete precipitation. A tiny bit, and this is really a tiny bit, 8.28 times 10 to the minus 9 molar, which is nanomolar. 8.28 nanomolar is very, very small, right? What about if we added 0.200? If we added 0.200 hydroxide, which was what we calculated before this one, did we get complete precipitation?
Yes.
Well, can you calculate it and see? Did you calculate it? Calculate it and tell me, was it a complete precipitation with 0.200? Using the numbers that we got earlier. Yeah, so with 0.400 molar sodium hydroxide or hydroxide, we got complete precipitation based on the book's criteria, 99.9%. With 0.200 molar sodium hydroxide, what was the percent precipitation? Well, we could calculate the percent remaining. How much was the equilibrium calcium?
1.09
Was it hydroxide or fluoride? Sorry.
fluoride.
Fluoride. Sodium fluoride. No. Sodium fluoride. 1.09.
0.98, I think it's 93.
Percent precipitation is just 100% minus this percentage. What does it come out to?
98.9.
98.9. Does that qualify as a complete precipitation? No. Right? And so this is what we call incomplete precipitation. And so 0.200 molar sodium fluoride was not enough to get complete precipitation, whereas 0.400 is enough. Actually, we don't need 0.400. We could have less than that, and it would be classified as complete. Now, to have 100% precipitation, what would be required? An infinite amount. Okay, let's look at fractional precipitation. Next. We did this in the lab. For example, we wanted to separate the 2+ ions, something like magnesium 2+, from the 3+ ions. How can we precipitate out one but leave the other in solution? And so how did we do that in lab? We precipitated it out as remember, how did we precipitate out one but leave the other? Yeah, controlled the pH. By controlling the pH, we were able to precipitate out iron and leave the magnesium in solution. And we precipitated those out as what was the precipitating agent? It was ammonia, but essentially we're precipitating out the hydroxides. And so the pH is going to change the amount of hydroxide in solution. And so in a fractional precipitation, this is what we do. We start off with, very, very little hydroxide. Can we completely get rid of hydroxide in water? No. And then what we're going to do is we're going to increase it. Well, very, very little hydroxide means we're going to start off at low pH or high pH. Very little hydroxide means low pH, which means very acidic. And so we're going to start off very acidic and then start to increase the pH, increase the hydroxide, decrease the hydronium. And so as we do this, then do this. Now, what we want to do is we want to keep increasing it, and then eventually we want to start to precipitate one. Which one are we going to precipitate first? iron 3? Why would we precipitate the iron 3 first? Or do we precipitate out both? Because both of these are insoluble. Magnesium hydroxide and iron 3 hydroxide are insoluble hydroxide. So don't they both precipitate out at the same time?
The iron and 10.
No, because there's a big difference in the solubility. If we look at the KSP for magnesium hydroxide, the KSP is, does somebody have their book? Add this written down. There we go. Let's take it.
.5 times 10 to the negative 11.
1.5 times 10 to the negative 11, thanks. And then the KSP for iron 3 hydroxide? Ten to the negative 38. At least somebody told me this. 4 times 10 to the negative 38. I'll wait for verification.
2.79 times 10 to the negative 39.
From our book?
No, that's right. That's right.
This is right. All right, 4 times 10 to the negative 38, 1.5 times 10 to the minus 11. Can we just look at the KSPs and tell which one's more soluble and which one's less? Yes or no? No. The reason is because of how it ionizes, right? Sometimes it's the square root, sometimes it's the cube root, sometimes it's the fourth root of the KSP, the solubility is. And so usually we can't compare them directly. However, in this case we might be able to because there's such a big difference here, you know. When you look at this, which one looks a lot less soluble? The iron. But again, be careful because of this nonlinear thing. The best thing is just go ahead and calculate it. You know, setting up an ice table like we did before. So it looks like iron's less soluble. And so what's going to happen is this. There's something called QSP, which is the same thing as QC and QP. Do you remember Q from chapter 15? Yeah. We calculate QSP based on the givens. So if QSP is greater than KSP, that is, if the given concentrations are greater than the equilibrium, then we have too much product. Because the QSP, the KSP equations for this would be magnesium hydroxide, solid, goes to magnesium 2 plus 2 hydroxide. And so if we have too much product in there, then what's going to happen? Shift left, which is called, shifts the reactants. The reverse direction is called precipitation or dissolution? Precipitation. So if QSP is greater than KSP, we get precipitation. If QSP is equal to KSP, then we're at equilibrium, right? Nothing's going to happen, so no precipitation. And if QSP is less than KSP, then still nothing's going to happen. Because, in other words, we call this, in terms of KSP, we call it a saturated solution when QSP is equal to KSP. And then when QSP is less than KSP, we call it an unsaturated solution. And so you could dissolve more if you want, if you have some more. But if you don't have any more, then you're going to have an unsaturated solution. Well, right now, here, we have an unsaturated solution because we don't have enough hydroxide to saturate it. Right? In other words, we got a fixed concentration of magnesium 2+. Let's keep it at 0.100 molar, magnesium 2+, the iron at 0.100 molar. And so the problem is the hydroxide's not concentrated enough to bring it up to saturation. So we got an unsaturated solution. So, for example, magnesium hydroxide, this is going to equal the magnesium concentration times the hydroxide ion concentration squared. And so the magnesium concentration is 0.100, and so we just don't have enough hydroxide to saturate this. Very little hydroxide. Whereas over here, this is going to equal the iron 3+ concentration times the hydroxide ion concentration cubed. Okay, but as I add more hydroxide, what's going to happen is eventually the hydroxide concentration is going to build up and QSP will equal KSP. When QSP equals KSP, we call that saturated. Now, if you keep adding more hydroxide, you're going to get supersaturated, which means it's going to start to precipitate. And so in a fractional precipitation like this, the calculations that we do is this. We calculate the hydroxide ion concentration required for precipitation. And so for magnesium, the hydroxide ion concentration required for precipitation is anything more than saturated. And so anything more than saturated is going to look like this. We have hydroxide. The hydroxide concentration should be greater than the KSP divided by the magnesium ion concentration. And we'll take the square root of that. If it's equal, if the hydroxide concentration equals this, then it's saturated. It's got to exceed it in order to precipitate. That's required for precipitation. For iron 3+, the hydroxide concentration required for precipitation has to be greater than the KSP divided by the iron 3+. And here we're going to take the cube root of this. And so let's see which one requires more, which one requires less. And so calculating this, you'll just plug in the KSP, which is over there, 1.5 times 10 minus 11 divided by 0.1, take the square root of that. And what is the hydroxide ion concentration required to precipitate out magnesium ion? Times 10 to the negative 5 molar, which gives us a POH equal, since you have it in your calculator, just take the negative log of that.
4.91.
4.91, which gives us a pH of
9.08.
okay, 4.9 what? 4.91 0? Okay, it can't be. Got to be some number here. I want to see the round off because this is 2 sig figs. This is 2 sig figs. I want to see an extra fig there. Sig fig. What about 9.08? 9.08 what?
Oh, it's 8 again.
8? 8? All right, we'll just go with 2 here. So, in other words, I need a pH greater than 9.08. 8, right? A pH of 9.08 will just saturate the solution in terms of magnesium and hydroxide. I need a higher pH. i.e. more hydroxide. What about for iron 3? Can someone do the calculation here?
times 10 to the negative 19.
6.32 times 10 to the negative 19 molar. Okay, so I need a hydroxide concentration greater than that. If I have a hydroxide concentration equal to this, it's saturated. Which means, what is the pOH of this? Must be some error. 18 is a bit high. Can somebody double check? Can you double check this one more time?
Concentration of hydroxide to precipitate iron, I got 7.36. 10 to the negative 13.
7.36 times 10 to the negative 13. Okay. 7.36 times 10 to the negative 13. That sounds more.
pOH is 12.13.
pOH is 12.13. Give me one more digit. 2. And the pH would be 1.868. pH of 1.868. pH of 1.868 is really low, really acidic. Where is the hydroxide coming from? In other words, I have to maintain a pH lower than 1.868 to prevent precipitation. A pH of higher than 1.868 has enough hydroxide to precipitate out the iron 3. But that's acid. Acid is hydronium, not hydroxide. And so where is all this hydroxide coming from? Where are you going to get hydroxide in a strongly acidic solution?
From the water.
Yeah, from the water. And so the tiny, tiny bit of hydroxide that's generated by water in an acid solution is enough to start to precipitate out the iron, which tells me that iron 3 is
More solid.
no. It precipitates as a hydroxide and acid. How can iron 3 precipitate out as a hydroxide and acid? Where's the hydroxide and acid? Well, it's coming from water, which tells me that iron 3 hydroxide is, you would say, insanely insoluble, or, just incredibly insoluble, which kind of makes sense because 10 to the minus 38. This stuff is not soluble, and therefore even trace quantities, tiny bits of hydroxide from the collisions in water are enough to precipitate or begin precipitating it out. And so in this case, it's for sure that iron 3 is going to precipitate out first. And so what we need to do is we need to maintain a very low pH. And so let's start off at like pH 0. If we start off at pH 0, is anything going to precipitate? No, because it's unsaturated. And then we're going to increase the pH. As we increase the pH, then when we hit a pH equal to 1.868, then what have we done? Now we have enough hydroxide to begin precipitating out the iron. I just need to add a little bit more. And so if I continue to increase the pH, add a little bit more hydroxide, then the iron 3 hydroxide begins to precipitate. Solid begins precipitating. How about the magnesium? Is the magnesium going to precipitate out in acid? No. The magnesium, you require a lot of hydroxide to precipitate that out because it's not nearly as insoluble. In fact, we need a fairly high pH, a pH of 9.08. to start precipitating out the magnesium. And so what this does is this gives us a method for separating the iron from the magnesium. The way we separate out the iron from magnesium is this. As we increase the hydroxide, the iron 3 must decrease in order to equal the constant. And so the bigger the hydroxide becomes, the smaller the iron 3 that can be sustained in solution is, and the more that's got to precipitate out. And so what we're going to do is we're going to continue this. You know, we're going to just keep adding more hydroxide until the pH hits what? What's the maximum pH that we want to go to? The maximum pH is a pH of 9.088. This is where we stop. Stop at pH 9.088. Because what we do here is, if we stop at this pH, then the magnesium becomes saturated with hydroxide. And so now just a little bit more hydroxide will start to precipitate out. Because if we continue here, increasing the pH, then both iron 3 and magnesium 2 plus precipitate. If both precipitate, then we don't want that because we want to separate the iron from the magnesium. But the problem is we didn't capture all the iron. At this point, there's still some iron left, right? In fact, it's impossible to capture all the iron because how much hydroxide do we need to get all the iron out? Infinite. And therefore, it's impossible, right? And so we have to sacrifice this. This has to leave a little bit of iron in solution. And so what we got to figure out is, what is the percent iron 3 plus remaining in solution at this point? We know it's got to be a lot smaller than 0.1 because as the hydroxide goes up, the iron has to go down. And so to calculate the percent iron 3 plus remaining in solution here, it's the iron 3 plus at equilibrium divided by the iron 3 plus initial times 100%. Now, how much iron 3 plus is there at equilibrium? The way we're going to calculate it is this. The iron 3 plus at equilibrium is just equal to KSP, which is equal to the iron 3 plus at equilibrium. But we know what the hydroxide concentration at equilibrium must be. The hydroxide concentration at equilibrium here has got to be pH 908. pH 908 is 1.22 times 10 to the minus 5 molar. And so this is going to be this. The hydroxide, oh, actually, you know what the hydroxide is. The iron 3 plus at equilibrium is equal to the KSP over the hydroxide ion Q. And so we just plug in the KSP, and for the hydroxide, we're using the stopping point hydroxide, which is 1.22 times 10 to the minus 5. Which means that the iron 3 plus concentration at equilibrium at the stop point will be what? So can somebody calculate it? KSP 4 times 10 to the minus 38 divided by 1.22 times 10 to the minus 5 cubed.
Is it 2.2 times 10 to the negative 22?
2.2, give me one more digit. 0 times 10 to the negative 23 molar. That sounds about right. Did other people get that? Okay. And therefore, the percent remaining at the stopping point is equal to 2.20 times 10 to the minus 23 over the original 0.100 times 100%, which is 2.20 times 10 to the minus 20%, which means the percent precipitation. Can you calculate the percent precipitation? The percent precipitation is equal to 100% minus 2.20 times 10 to the minus 20. Go ahead and calculate that in your calculator. You can for me.
100.
100? No, it's not 100.
Round off.
Yeah, that's what you get on your calculator. You need to buy a more expensive calculator. Your calculator's not good enough. Well, it's going to be, I mean, this is so little remaining. 10 to the minus 23 molar is nothing, right? And so essentially it is 100%, but let's go ahead and calculate what it is. So we're going to have to calculate by hand. So this is going to be 0. I need 19 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 19 zeros and a 2, 2, 0. And so this is going to be 99 point. How many nines do I need? A lot. And so essentially 100%. But, you know, just because the calculator gave you 100% doesn't mean you should round it to 100%. I want to see the rounding stuff. You know, anyway, the thing is, you know, there's a big difference between this 100% that your calculator gave and somebody rounding this. You know, 99.5, what do you round that to? You round it to 100%, right? And so there's a big difference. All right, so that was pretty good because pretty much we got all the iron out, leaving, you know, such a small quantity, you couldn't even measure it left in solution. Okay, that's the idea behind fractional precipitation. Now, we're going to talk about today's lab. Next. Today's lab I'm going to change around a little bit because I didn't want to use the whole lab period for it. And so we're just going to get familiar with the pH meter, the pH probe, in preparation for Tuesday's titration lab. You know, on Tuesday we should come in, quickly calibrate it, and get everything set up, ready for the titration. This is a very time-consuming lab, Tuesday. And so that being the case, what you're going to do is you're going to set up the pH meter, calibrate it with a pH 4 and a pH 7 buffer. No, everybody in my morning class has used a pH meter before. Has everybody used one here? Pretty much? Yeah. And then we're going to measure the pH of some solutions back there. You know, you could just pick a few, 2 or 3 solutions, just to get some practice measuring pH. You might have done this in Chem 1A as well. And then in the second part, we have the buffer, right, that we're going to deal with. And I'm going to change that a little bit. And so let's see what solutions we're measuring the pH of. You know, what are your choices? Your choices are sodium chloride. What's a calculated pH? You know, we're going to measure the experimental pH, but what's the pH you would calculate for sodium chloride? Yeah, pH is 7. What's the next one? That's because sodium ions and chloride ions are neutral.
HCl.
HCl,
6 molar HCl.
is it 6 molar or 0.1 molar? Okay.
There's ACL on M1.
Oh, HCl is not molar. All right, 0.1 molar sodium chloride, 0.1 molar sodium acetate. You know, we did sodium acetate before. Remember that calculation for sodium acetate? We did Kb. Do we have to worry about Kw? Would you worry about Kw? Yes or no? No. I mean, Kw. Kb is enough. And so the pH, you know, pH should be greater than 7, right? It's a basic salt. And to calculate it, use Kb. Okay, what's the next one? Okay, 0.1 molar ammonium chloride. Ammonium ions are acid, Ka. Chloride is neutral. And so the pH should be less than 7, and we calculate the pH using Ka. Would you worry about Kw, adding a little bit more hydronium? Kw? Yes or no? For 0.1 molar.
No.
Yeah, no, it's pretty concentrated. All right, what's the next solution?
Zinc chloride.
Zinc chloride. What do you think, pH 7? Like sodium chloride, zinc chloride, pH 7? No. No. Zinc chloride, the pH is actually less than 7. It's a little bit weird because metal cations except for group 1 and group 2, just throw group 2 in there entirely, can act as Bronsted acids. An example of this is iron. Iron 3 actually forms the hexa-aqua complex in water. And so we have hexa-aqua iron 3 ion. And if we look at the iron 3, those waters are covalently bonded to the iron like this. And what that does is it changes the electronic environment around the hydrogens. Because iron 3 is pulling electron density, is a high positive charge, so pulls electron density from the oxygen, which in turn pulls the electron density from the hydrogen, making the hydrogens a lot more positive than you'd expect, like in water. And so these waters behave a lot differently than a normal water does. These waters are a whole lot more acidic. We call this the inductive effect, you know, where electron density is being sucked off. Well, if these hydrogens are a lot more acidic, then there could be a collision with the water molecule, generating hydronium. So the water can pluck off one of the hydrogens, and we're left with this. One of the aquas is converted into hydroxo. And so we get like a penta-aqua hydroxo iron 3 ion with a net charge of 2+. This is, what kind of a reaction is this? No. Not a redox. It's acid base. Or another way of saying this is a Ka reaction, acid plus water. It's an acid hydrolysis reaction. The Ka for this is bigger than the Ka for acetic acid. If the Ka for this hexa aqua iron 3 ion is bigger than acetic acid's Ka, then which one's a stronger acid? Iron 3. And so this iron 3 ions in water is more acidic than acetic acid at a given concentration. And so in order to calculate, we need the Ka for Zn2 plus Aq. You know, I don't know, is that the tetra aqua? The hexa aqua? We'd have to look it up. Or maybe the diaqua? Look that up. Okay, what's next? Sodium carbonate. You know, sodium ions are neutral. However, carbonate is what we call a monobasic base, dibasic base, tribasic base, dibasic base. And so for carbonate, we got Kb1, Kb2, and Kw. Kb2 is not so huge, so probably we're okay with just using Kb1 for this. Figure out the pH. Kb2 is not so big in magnitude. And so anyway, the pH should be greater than 7. Sodium carbonate is basic in water. Okay, what's next? Okay, potassium aluminum sulfate. Mixed cation salt. And so in potassium aluminum sulfate, we have potassium ions. Are potassium ions acidic? No. Potassium ions are neutral. How about aluminum ions? Are aluminum ions acidic? Yes. Aluminum ions, Aq, are acidic. Aluminum forms the hexa aqua complex. And so just like iron, it can hydrolyze water to form hydronium and what? Penta-aqua, hydroxo, non-aluminate, aluminum 3. The Ka for this is, actually I should have this still up, I hope. Yes, it's there. Oh, I left it off. Do you still have the K? What was that, Appendix D you were looking at? I'll look it up. Just 1 second. 1.1 times 10 to the minus 5. Acetic acid is 1.8 times 10 to the minus 5. Which one is more acidic, acetic acid or aluminum ions? Acetic, but not by much. I mean, they're pretty close, right? So this is a comparable acidity to acetic acid. Interestingly enough, iron 3 and aluminum are considered polyprotic acids because they have more than one water. And so what can happen is there could be a Ka2 and a Ka3. It stops at Ka3 because we form the hydroxide in both. Aluminum hydroxide here and iron 3 hydroxide. But we're only going to worry about Ka1 for now. How about sulfate? What is sulfate? Sulfate is a base. It's a dibasic base, which means there's a Kb1 and a Kb2. How can we figure out what the Kb's are? Well, from the conjugates. And so, you know, sulfuric acid, you know what Ka1 for sulfuric acid is? Very large. Ka2 is kind of big. Ka2 is significant, so we should worry about it. It's 0.01. 0. And then we have Kw. Right? And so today's quiz is going to be a calculation. Today's quiz, I'd like you to, oh boy. Hang on. Today's quiz is calculate the pH of 0.100 molar KAlSO4 2. And so even though this is not a reactions quiz, the same rules will apply. You can talk with your neighbors, you can use whatever resources you have. However, you can't ask any of the other instructors for help. All right, so go ahead and get to it, and then we'll do an abbreviated pH lab today. Okay?
Should I write on a piece of paper?
Yeah, write it on a piece of paper and then you'll turn it in.